Let us start this video by asking you a question. Say that you have an alarm clock rated at around 30 decibels, but it's failing to do its job, that is wake you up every day. So you think that maybe if I buy another alarm clock rated at around the same level, that is 30 decibels, the resulting sound will be twice as loud, that is 60 decibel. But are you sure of that? You guessed it, the answer is no. And I promise this is related to logarithms. Let us first understand what do we mean by taking logarithms or log. Firstly, we have got the definition or explanation that is written in almost every mathematics book out there. We are all familiar with the equation 2 cube is equal to 8 or 2 to the power 3 is equal to 8. However, we can also represent this equation in the form of a logarithmic expression, that is, the log of 8 with the base 2 is equal to 3. Here, 2 is known as the base. It is quite important while evaluating the logarithm, as different values of the base can yield different results of the logarithmic expression. Thus, when we say the log of some number c to the base a is equal to b, we actually mean that a to the power b is equal to c. Sometimes you may also see that there isn't any base mentioned as such. For example, log of m, no base mentioned. It is understood that the base is actually 10. Therefore, when we see that it's written log of m is equal to c, it is implied that 10 to the power c is equal to m. You may also see sometimes log represented as ln. For example, ln of n. In this case, the base is actually Euler's number, that is e. Therefore, if it is written that ln of n is equal to d, it is implied that e to the power d is actually equal to n. Fun fact, this Euler's number is actually an irrational as well as a transcendental number, similar to pi. Happy Pi Day, by the way. This number was chosen for the natural log for various reasons, but that's a topic for another video. Do let me know in the comments whether you would like a video explaining the significance of the Euler's number. Now let us come back to the original question that I asked at the beginning of this video. If you ring two 30 decibel alarm clocks together, what do you think will be the loudness of the resulting sound? Will it be 13 to 60 decibels? Or perhaps just 30 plus 20 is equal to 50 decibels in total? The real answer is surprisingly close to around 33 decibels. To understand this, we need to understand the units bell and its cousin decibel. They are both a logarithmic scale. To understand this, we need to understand how this unit came into being, that is, how do we measure loudness according to the intensities of the sound. The loudness in bell is equal to the log of I by I naught with the base 10. But if you want to calculate the loudness in decibels, just multiply the whole thing by 10 and the formula becomes 10 into log of I by I naught with the base 10. Here, I naught is the intensity of sound we are taking as a standard, and I is the intensity of the sound whose loudness is to be measured. So now if we take two alarm clocks, I becomes 2I naught. And after solving the equation, wait for it, the increase in the loudness is approximately equal to 3 decibels. Thus, the new loudness is equal to 33 decibels. However, you may say that this is just how we chose to measure loudness. But logarithms do occur fundamentally in many places in nature. For example, hear this tune. Now this one. And at last this one. Do they sound similar? Musicians may answer this question like this. This tune is one octave higher than this one, and this one is one octave lower than this one. But this is the part where it really gets interesting. The frequencies that were played were 256 Hz, 512 Hz, and 1024 Hz respectively. You can clearly see that the frequencies, if plotted on a graph, are not equally spaced. However, your brain makes this arrangement linear by taking the logarithm in each case. And this is not something we as humans chose to do. This is a result of billions of years of evolution. An important consequence of this is the inability of the human beings to grasp the concept of exponential growth. We tend to linearize every data that we see. This is actually the automatic application of logarithms by our brain, and this can be pretty dangerous in some cases. Take this pandemic for an example. If you see the graph of the total number of edit cases each day, or even the graph of the daily cases, you will find, at least for some period of time, that the graph has an exponential nature, like this. And our inability to grasp this concept of exponential growth is what makes a pandemic so dangerous. In real life, it isn't linear. That is, if we have, for example, 2 cases at the start, it isn't like we will have 4 cases the next day, then 6 cases, then 8 cases, then 10, 12, 14. It isn't like that. In real life, it is exponential. That is, for example, if we have 2 cases at the beginning, the next day we can have 4 cases, but then we'll have 8 cases the next day. Then 16, 32, 64, 128, and then the whole thing explodes suddenly. Quick trivia for those who are watching. Try to answer in the comments why the daily cases and the total number of cases each day have the same nature of graph, that is exponential. So we can conclude that logarithms are quite a lot useful in real life. So that's it for today. I hope you liked this video. Subscribe to this channel and hit the bell icon to get notified of any future uploads. My name is Pranjal Gupta and you're watching String Theory. See you guys on the next one.